So today we are going to talk about a specific case of greedy algorithm, which is the Prim's algorithm. So what does Prim's algorithm try to do? It tries to solve a very practical problem. It tries to connect n points in the cheapest way possible so that there is a connection between every pair of points. If you were to represent this problem using graphs, you would see that each point becomes a vertex within the graph. Each connection is an edge, and the costs associated with those connections are the weights of those edges. So now the question itself can be posed as a minimum spanning tree problem, right? So for those who are not familiar with the concept of minimum spanning tree, a spanning tree of a connected graph is its connected acyclic is the key term, acyclic subgraph or a tree that contains all the vertices of the given graph, right? A minimum spanning tree is a special case of a spanning tree which has the lowest total weight. So really simple. Okay, yeah. Before we get into Prim's algorithm, let's try to understand why Prim's algorithm is needed, right? So why not just try an exhaustive approach and generate all spanning trees for a given graph? We cannot do that mainly because, or we rather should not do that mainly because generating spanning trees is not a scalable process. So as the size and density of a graph increases, the number of spanning trees that can arise out of it grows exponentially. And at the same time, interestingly enough, it's way harder to generate all spanning trees of a given graph than it is to find out the minimum spanning tree of a given graph. It's counterintuitive, but yeah, that's how it is. So, okay, so that's why we need Prim's algorithm, right? So how does Prim's algorithm work? So Prim's algorithm constructs a minimum spanning tree through a sequence of expanding subtrees. The initial subtree itself in such a sequence would be a randomly picked out vertex. You can pick out any vertex, it doesn't really matter from the set of vertices that are there in the graph. On each iteration, you would expand the current subtree by attaching to it its nearest vertex. What do we mean by a nearest vertex? A nearest vertex would be that vertex which is outside of the tree, but is connecting to some vertex within the tree with a minimum weight edge. Right? And if there are two edges which have the same weight, then ties can be broken arbitrarily. So the algorithm stops after all of the graph's nodes have been added into the subtree, which will end up being your minimum spanning tree, right? So you'll see the algorithm, how it looks now.